So this set of lectures is going to talk about chemical bonds. So basically, how do we put atoms together? So if you recall from what we've talked about previously, we talked about the shell model before. So if you remember the shell model, that is that idea that the electrons kind of live in those concentric circles around the nucleus. And you've got the first shell that can hold 2 electrons maximum, the second shell that can hold a maximum of 8, and so on. So that number on the shell in this model indicates the maximum number of electrons that that shell / level can contain. And also remember that it's tied to the periods in the periodic table, as far as shell 1 matches period 1, shell 2, period 2, and so on. So why are we looking again at the shell model? Well, those electrons are the thing that determine the property of the element. So the number of electrons that are in the outermost shell are the ones that are going to determine the properties of the element. So if you remember, when we talked previously about the periodic table, each of these columns or families have similar properties, and it's because of the number of electrons in their outermost shell. So for example, over here, we've got pulled out the first 3 elements out of the noble gases. And so these guys have the same configuration in that outermost shell. So you can see that the first shell for helium has 2, so that means that that first shell is fully occupied. If we look at the next one down, which is neon, neon has the first shell full, but also its second shell is full, because that second shell can hold a maximum of 8. And then we move down one more, argon, same thing. All of the shells are full. And so elements in the same group are going to have the same configuration of electrons in those shells. So let's take a look at why we care about this. Because with noble gases, remember, these guys are the ones that are unreactive. And so they're not going to interact with other elements. And this actually right here is why. These shells are full. So what we're going to be talking about for most of what we're going to be looking at are what we call valence electrons. So valence electrons are the electrons in the outermost shell that participate in chemical bonds. So in those noble gases, that outermost shell is full. So there aren't any electrons to participate in any chemical bonds. They aren't missing any, so they don't have any to be able to share or give away, so they're not going to participate in any sort of bonding. The elements that I have here, though, these guys have unpaired electrons, which are represented by these dot diagrams. And so you can see we don't show all of the different shells. So chlorine does have another shell. It has the first shell with the 2 electrons in it. We only show the valence electrons when we draw these dot diagrams. So that outermost shell of the ones that we're concerned about. And so we're looking here, we've got paired electrons. So these 2 are sitting together, these 2 and these 2, but we have 1 unpaired electron. So there are 7 electrons in chlorine, 1 that's by itself. And this is the one that's actually going to do any sort of participation in bonding, because what these atoms want is they want this valence shell, this outermost shell, to be full. And they want all of these to be paired up. So we want all of those electrons in that valence shell to be paired in sets. So you can see carbon. We've got carbon here, and in its outermost shell, or it's in its valence shell, it's got 4 electrons, and they don't sit in pairs. So it's got 4 unpaired electrons. And so this is going to be able to have 4 interactions with other atoms in order to make chemical bonds. So let's take a look at the major part of the periodic table and what these dot diagrams look like for them. So here we go. So there's carbon, the one we were just looking at. So you can see that there's the 4 dots around it. And here's the chlorine that we were just looking at with its 6 dots, and then it's 1 friend by itself. And what you can see is that for each of the families, they have the same electron dot diagrams. So all of family 1 has 1 unpaired electron in its outermost shell, no matter which one we're looking at, no matter which period. So 1 electron for hydrogen, 1 for lithium, even though this one would be in the 2nd shell, 1 for sodium, even though that's in the 3rd. This one would be in the 4th, the 5th, and the 6th. So these guys are going to all have 1 outermost electron. Then the 2nd family, if you notice, these numbers match up for these guys. Now, this number doesn't match for 3 for this, but if you look at your periodic table, this is family 3A. 3 for 3 unpaired electrons, or 3 electrons in the outermost shell. 4A for 4 outermost electrons, 5A, 6A, 7A, 8A. Obviously helium's the exception because it only has 2 electrons, so it can only fill that first shell. But those A numbers match the number of valence electrons in that outermost shell. And again, these valence electrons is what gives these elements their properties and why they all act very similarly. So let's take a look at how these electrons can work to start to make bonds. So the first thing we're going to look at is what we call ions. So this is the first way that atoms can start to work to make bonds. So what we're looking at here is the formation of an ion. Now, what atoms want to do is they want to have their outermost shell full. So they want this outermost shell to be full of the electrons. So they want to have 8. They want 4 pairs. Now, sodium here, you can see sodium has 1 just lone electron by itself because sodium has 11 electrons when it starts. The thing is in order for it to be a stable, happy atom, to be able to have that outer shell with the 8 in it, it has 2 options. One is it can find 7 electrons, or it can lose the 1. And it's easier to lose this 1. So it's easier to take this guy and get rid of it than it is to try and find 7 to add in. And so that's what it does. So ions are atoms that have lost or gained 1 or more electrons. So in this case, sodium loses that 1 electron. And so this valence shell becomes empty. And now the next shell in is full. And this is now going to be a very stable atom because it's got that full outer valence shell. But it becomes an ion because now it has a charge. So you can see here that sodium becomes a +1 ion. This is because it's still going to have its 11 protons in the nucleus that it started with, but now there's an imbalance in the charge. It had 11 electrons, so they canceled each other out over here. So they had a 0 net charge. But now there's 1 more proton than there are electrons, so we now have a positive charge of 1. If this was, for example, calcium, So if I go back, so calcium has 2 outer electrons. Calcium is going to do the same sort of thing. Calcium is going to get rid of these 2 electrons, and it's going to become a 2+ ion, because it's going to have a difference of 2 protons versus the electrons, because it's lost 2 electrons, so it has 2 more protons than it has electrons. So that's the case for this entire group. This entire group will become +2, and this entire group here is going to become +1. So that's how you get a positive ion. Negative ion is just the opposite. So negative ions are formed when you get an atom that's just missing 1 or 2 electrons. So this guy has 7, it's fluorine, and it's going to need just 1 electron. It's easier for it to find an electron and add it in than it is to get rid of all 7 of these. And so that's what it does. It's going to gain an electron, probably from something like sodium or calcium, one of those guys that's getting rid of them. So it's going to gain that electron. It now has that filled outer valence level. And now we get a negative ion, because fluorine started off with 9 protons and 9 electrons. So again, a 0 net charge. But now, because it gained that electron, we have 10 electrons versus 9 protons. So we have 1 more negative charge. And so that gives us a -1 charge. And so if we look back at the periodic table here with the electron dots, here you can see fluorine. So fluorine is in the group that does this. Any of these guys will become -1. This group sometimes can become -2. They don't commonly. We'll see what these elements do, as well as this group and this group. They tend to do something different, but this group can become a -2 ion at times. All right, so that's the formation of ions, and we can actually guess who's going to make what kind of ion based on where they're located on the periodic table, because of where they are and which way they're going to go. So you can see here, these first 2 ones, like I was showing you, so family 1, family 2, those 2 are definitely going to become positive ions. Pretty much all of the transition metals are going to become positive ions. So they have a very, as you can see over here, they have a very weak attraction for those electrons. So they don't tend to hold on to the ones that are farther out. And so they will tend to give them up, mainly because they only have 1 or 2 of them in that outermost ring, that outermost shell. As we come to the right, these guys are going to tend to make negative ions, just like I was showing you. So we've got fluorine and the other members of their group, the halogens, they're going to make negative ions. Like I said, the chalogens, these guys like the oxygen and so forth, they will make -2 ions sometimes. We've got these guys in the middle here. So they can make positive ions or -4 or -3 ions, but they tend to not do it very much. The table here says that they can have a tendency to do it, but you can see that they're kind of in that in-between color between the orange and the blue. So they are in this in-between area. They tend not to make ions. All right, so that's our introduction into valences, and then the next video is going to actually talk about the different types of bonds.